According to Section 300.5 Exception 3 of the National Electrical Code, a feeder circuit installed at a depth of 12 inches or more and rated for less than 15 amps and 300 volts can be considered a feeder calculation rather than a service entrance calculation. For voltage drop calculations using the uniform spacing equation, also known as use, the voltage used is the nominal voltage, which is typically the rated voltage of the equipment. In this case, the nominal voltage is 57 volts AC. The definition of a service entrance in Article 100 of the NEC is the conductors and equipment that connect the service entrance conductors to the building or other structure. The service entrance conductors are the conductors that bring electricity into the building from the utility. In this case, the 57 volts AC input is not coming from the utility but is being generated by the wind units. Therefore, it would not be considered a service entrance. Instead, it would be considered a feeder circuit. Based on the provided information, the 57 volts AC input would be considered a feeder calculation for direct burial using use number 6 in conduit for voltage drop calculations. It does not qualify as a service entrance since it is not supplying electricity from the utility. To elaborate further on feeder versus service entrance considerations, it's crucial to understand the distinction lies in the source of the power. A service entrance brings power from the utility company to the building, while a feeder circuit distributes power from a source within the building or from a separate on-site generation system like these wind turbines to a load or another distribution point. Now, diving into the NEC, the National Electrical Code, Section 300.5 provides requirements for the installation of underground conductors. Exception 3 specifically addresses scenarios where a feeder circuit meets certain criteria, allowing for a reduced burial depth of 12 inches. These criteria are less than 15 amps, less than 300 volts, and being a feeder circuit. This exception is beneficial in situations where shallow burial depths are desired or are necessary, but it's essential to strictly adhere to all the conditions outlined in the exception. When performing voltage drop calculations, it's also important to understand the impact of conductor size, length of the run, and the load current. The uniform spacing equation, use, is a simplified method for calculating voltage drop, especially useful for preliminary estimations. However, more complex calculations may be necessary for long runs or critical applications. Remember that voltage drop can significantly affect the performance of electrical equipment, so it should always be a key consideration in the design and installation of electrical systems. Furthermore, it's imperative to select the correct type of conductor for direct burial applications. Use, which stands for Underground Service Entrance Cable, is specifically designed for this purpose. It has a moisture-resistant insulation and is suitable for direct burial without the need for additional protection such as conduit, although in this case, conduit is being used. However, local codes and regulations should always be consulted to ensure compliance with all applicable requirements. The 3-pole disconnect located just inside the building serves as a crucial safety feature, allowing for the complete isolation of the wind turbine system from the building's electrical system. This disconnect should be readily accessible and clearly labeled for emergency situations and maintenance purposes. 3-phase alternating current, or AC, systems are commonly used in wind turbine applications due to their efficiency and ability to deliver a constant power output. The 57 volts AC voltage level is relatively low, which enhances safety and simplifies the design of the electrical system. However, it also means that higher currents are required to deliver the same amount of power compared to high voltage systems. Therefore, careful attention must be paid to conductor sizing to minimize voltage drop and prevent overheating. In conclusion, when evaluating whether a 57 volts AC input from wind turbines qualifies as a service entrance or a feeder, it's essential to consider the source of the power, the applicable NEC sections, and the specific characteristics of the electrical system. In this case, since the power is generated on-site and not supplied by the utility, it's classified as a feeder circuit, allowing for compliance with Section 300.5 Exception 3 of the NEC and enabling a shallower burial depth of 12 inches. Moreover, proper voltage drop calculations, conductor selection, and safety measures such as the 3-pole disconnect must be implemented to ensure the safe and reliable operation of the wind turbine system. The importance of consulting the local authority cannot be overstated. The authority having jurisdiction, or OJ, has the final say on interpreting and enforcing the NEC and local electrical codes. They can provide valuable guidance and ensure that the installation meets all applicable safety standards. Furthermore, documenting all aspects of the installation, including calculations, wiring diagrams, and inspection reports, is crucial for future maintenance and troubleshooting. A well-documented system makes it easier to identify and resolve any issues that may arise over time. Also consider the impact of environmental factors on the electrical system. Direct burial conductors are exposed to moisture, temperature fluctuations, and potential physical damage from soil shifting or digging. Therefore, it's essential to select conductors that are specifically designed for direct burial and to follow proper installation techniques to minimize the risk of damage. Another aspect of feeder design involves calculating the conductor ampacity. Ampacity refers to the current carrying capacity of a conductor, and it must be sufficient to handle the maximum load current without overheating. The NEC provides tables that specify the ampacity of various conductor sizes and types, taking into account factors such as insulation temperature rating and ambient temperature. It's crucial to select a conductor size that has an ampacity greater than or equal to the calculated load current, with appropriate derating factors applied for ambient temperature and the number of conductors in a raceway. Finally, proper grounding and bonding are essential for safety and to prevent electrical shock hazards. Grounding refers to connecting the electrical system to the earth, providing a lower impedance path for fault currents to flow back to the source. Bonding refers to connecting all metallic parts of the electrical system together to create an equipotential plane, minimizing the voltage difference between them. The NEC provides detailed requirements for grounding and bonding, and it's essential to follow these requirements carefully to ensure a safe and reliable electrical system. Also consider the type of conduit being used. While the question indicates the use of conduit, it's important to verify that the conduit is suitable for direct burial. Some types of conduit, such as rigid metal conduit, are designed for direct burial, while others, such as electrical metallic tubing, are not. If the conduit is not suitable for direct burial, it may corrode or deteriorate over time, compromising the integrity of the electrical system. In addition, the fittings and connectors used with the conduit must also be suitable for direct burial. These fittings should be made of corrosion-resistant materials and properly sealed to prevent moisture from entering the conduit system. Furthermore, the conduit should be installed at a depth that complies with the NEC and local codes. While Section 300.5 Exception 3 allows for a reduced burial depth of 12 inches for certain feeder circuits, the minimum burial depth for other types of circuits may be greater. It's essential to consult the NEC and local codes to determine the appropriate burial depth for the specific installation. Also consider the type of overcurrent protection being used. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. These devices should be properly sized and installed in accordance with the NEC and the manufacturer's instructions. In the case of the wind turbine system, the overcurrent protection devices should be sized to protect the conductors and equipment from damage due to excessive current flow. Furthermore, the overcurrent protection devices should be readily accessible and clearly labeled for easy identification and maintenance. Moreover, periodic inspections and maintenance are essential to ensure the continued safe and reliable operation of the wind turbine system. These inspections should include checking the condition of the conductors, conduit, fittings, and overcurrent protection devices. Any damaged or deteriorated component should be replaced promptly. In addition, the grounding and bonding system should be inspected to ensure that it is still intact and functioning properly. Regular maintenance, such as tightening connections and cleaning equipment, can help to prevent problems from developing and extend the lifespan of the electrical system. And remember, the NEC is not a design manual, but rather a set of minimum safety standards. While complying with the NEC is essential, it may be necessary to go beyond the minimum requirements to ensure the long-term reliability and performance of the electrical system. This may involve using larger conductors, higher quality components, or more robust installation techniques. The goal is to create an electrical system that is not only safe, but also capable of meeting the demands of the application for many years to come. Now consider the voltage rating of the equipment being used. The equipment connected to the 57 volts AC feeder circuit must be rated for at least 57 volts AC. Using equipment that is not properly rated for the voltage can create a safety hazard and damage the equipment. Furthermore, the equipment should be listed by a recognized testing laboratory such as Underwriters Laboratories or all to ensure that it meets applicable safety standards. Listing by a recognized testing laboratory indicates that the equipment has been tested and found to be safe for its intended use. Always refer to the manufacturer's instructions for proper installation and operation of the equipment. The manufacturer's instructions provide detailed information on how to install and use the equipment safely and effectively. Following the manufacturer's instructions can help to prevent problems from developing and ensure that the equipment operates as intended. Also consider the use of surge protection devices. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other electrical disturbances. These devices can help to prevent damage to sensitive electronic equipment and extend the lifespan of the electrical system. SPD should be installed at the service entrance and at any other locations where sensitive equipment is connected to the electrical system. Furthermore, the SPD should be properly sized and installed in accordance with the manufacturer's instructions and the NEC. Consider the coordination of overcurrent protection devices. Coordination refers to the selection and arrangement of overcurrent protection devices in a way that ensures that the device closest to the fault will trip first, minimizing the extent of the outage. Proper coordination can prevent unnecessary tripping of upstream overcurrent protection devices and improve the reliability of the electrical system. Coordination studies are often performed by qualified electrical engineers to ensure that the overcurrent protection devices are properly coordinated, and the importance of arc flash hazard analysis should not be overlooked. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit or other electrical fault creates a high-energy arc. Arc flash can cause severe burns, explosions, and even death. An arc flash hazard analysis is a study that assesses the risk of arc flash in an electrical system and identifies measures to mitigate the hazard. The results of the arc flash hazard analysis are used to determine the appropriate personal protective equipment, or PPE, that workers must wear when working on or near energized electrical equipment. In addition, the arc flash hazard analysis may identify changes to the electrical system that can reduce the risk of arc flash. Now think about the potential for future expansion. When designing the electrical system for the wind turbine system, it's important to consider the potential for future expansion. This may involve installing larger conductors, using a larger conduit size, or providing additional overcurrent protection devices. Planning for future expansion can help to avoid costly and disruptive upgrades in the future. Also consider the use of energy-efficient equipment. Energy-efficient equipment can help to reduce energy consumption and lower operating costs. This may involve using energy-efficient motors, transformers, or lighting fixtures. The use of energy-efficient equipment can also help to reduce the environmental impact of the wind turbine system. Consider the impact of electromagnetic interference, also known as EMI. EMI is a disturbance that can affect the performance of electronic equipment. EMI can be caused by a variety of sources, including electrical equipment, radio transmitters, and lightning strikes. To minimize the impact of EMI, it may be necessary to use shielded cables, filters, or other EMI mitigation techniques. Furthermore, the electrical equipment should be properly grounded and bonded to minimize the risk of EMI. And lastly, remember that electrical safety is paramount. Working with electricity can be dangerous, and it's essential to take all necessary precautions to protect yourself and others from electrical shock and other hazards. This includes wearing appropriate personal protective equipment, following safe work practices, and being aware of the potential hazards associated with electricity. If you're not qualified to work on electrical equipment, it's best to leave the work to a qualified electrician.